Hello everyone, myself Dr. Kamlesh Thakkar, Assistant Professor, Government Bilasa Girls PG College, Bilaspur. Welcome you all in the course of the Fundamental of Engineering Physics. Imagine standing on a beach looking out of over the vast ocean. The waves crash in rhythmic pattern, the tides ebb and flow, and yet beneath this seemingly simple scene lies the chaotic motion of countless water molecules, each moving unpredictably on its own. Now think about how despite this chaos we can predict the behavior of the oceans with remarkable accuracy, whether it is the height of the tides or the direction of the waves. This scenario mirrors what we face in physics when we deal with systems made up a huge number of particles like gases, liquids and solids. On one hand, the motion of individual molecule is complex and unpredictable. On other hand, the collective behavior of these particles follows predictable laws. Laws that govern the pressure in a gas, the flow of heat or the behavior of materials at different temperatures. But how do we bridge the gap between the unpredictable world of individual particles to the predictable behavior of the entire system? How can we make scenes of the chaotic motion of trillions of particles to understand the orderly behavior we observe? This is where statistical physics come into play. It is the branch of physics that allow us to understand predict the behavior of system with an enormous number of components by using statistical method. It helps us connect the micro level chaos with the macro level order, offering insight into the way system behave the way they do, whether we are talking about a cup of coffee cooling down or a star burning brightly in the sky or the random fluctuations in a stock market. Today, we will begin our journey into the fascinating world. We will explore how statistical physics provides a powerful framework for understanding everything from the basic properties of matter to complex phenomena in the natural world. By the end of this lecture, you will see how statistical physics not only answer fundamental questions about the universe, but also play a crucial role in the advancing technology and science in ways you might never have imagined. Let's dive into the fundamental concept of statistical physics, starting with the basic idea of microstate and macrostate and how they help us describe predict the behavior of large system. Let's begin with outline, and the outlines are: introduction, fundamental concept of statistical mechanics, probability distributions in statistical physics, unassemble in statistical mechanics, thermodynamics laws and their statistical interpretations, quantum statistical mechanics, phase transitions and critical phenomena, application of statistical physics in various fields, computational method in statistical physics and future direction in statistical physics. Now with introduction, statistical physics is a branch of physics that connects the macroscopic property of systems with the microscopic behavior of their constituents. These fields form the foundation for the understanding many phenomena in thermodynamics and quantum mechanics and beyond. Statistical physics is the study of large system where the number of particles is enormous, typically on the order of Avogadro's number. The challenge lies in the predicting the behavior of entire system based on the property and interaction of individual particles. Now, fundamental concept of statistical mechanics. To get started, let us introduce the concept of microstate and macrostates. A microstate is a specific detailed configuration of a system describing the position and velocity of every particle. On the other hand, a macrostate is characterized by macroscopic quantities like pressure, temperature and volume, which are averaged over many microstates. Microstates. A microstate is a specific detailed description of a state of system at the microscopic level. It accounts for the exact position of momentum, that means energy, of every particle in the system. If we see the characteristic of microstates, then unique configuration. Each microstate corresponding to a unique configuration of the system's components such as molecule in a gas. Probabilistic nature. Microstates are usually not observable directly in a large system because there are so many possible microstates equally likely. In many statistical physics problems, it is assumed that all accessible microstates of a system are equally likely if the system is in equilibrium. For example, consider a gas in a container. A microstate would specify the exact position and velocity of each molecule in the gas at a given instant. Now, macrostate. A macrostate is a description of a system at a macroscopic level, which is determined by macroscopic variables such as temperature, pressure, volume and number of particles. It represents an ensemble of microstates. Now, characteristic of the macrostate. Aggregate description. A macrostate does not describe the individual particle, but instead gives a statistical description based on observable quantity. Many microstates. A single macrostate can correspond to a vast number of microstates. The number of microstates associated with a macrostate is a measure of the macrostate's entropy, equilibrium. In equilibrium, the system will spend most of its time in the macrostates with the highest number of corresponding microstate. For example, the same gas in the container described by its temperature, pressure and volume is an example of macrostate. This macrostate can be realized by an enormous number of different microstates. Various ways the molecules can be arranged to give the same temperature and pressure. Now, what is the relation between this microstate and macrostates? So, in the terms of entropy, the number of microstates omega associated with the macrostate is directly related to the entropy S of the system by the Boltzmann formula, and the formula is S is equal to Kb In omega, where Kb is well known by the Boltzmann constant. Entropy is a measure of the number of microstates corresponding to a macrostates. Second is the probability distributions. In statistical mechanics, the probability of the system being in a particular microstate depend on the energy of the microstate and the temperature of the system. The distribution of microstate follows the Boltzmann distributions. Thermodynamic quantities. Macroscopic thermodynamic quantities like temperature and pressure are averaged over the microscopic properties of the particle in the system. Now, probability distribution in statistical physics. In statistical physics, probability distribution play a crucial role in describing the behavior of system composed of a large number of the particle. This distribution provides a way to predict the likelihood of different possible states of the system based on microscopic details. Now, the key probability distribution in statistical physics are: first, microcanonical distribution; second, canonical distribution, we well known with Boltzmann distribution; third, grand canonical distribution; fourth, Fermi-Dirac distribution, and fifth is Bose-Einstein distributions. First, microcanonical distributions. In isolated system with fixed energy, volume and number of particles, all accessible microstates of the system are equally probable if the system is in equilibrium. The probability pi of the system being in a particular microstate is pi is equal to 1 upon omega, is the total number of microstate consistent with the macroscopic constraint. Entropy. The entropy S of the system is related to omega by Boltzmann's formula, where S is equal to Kb In omega, where Kb is the Boltzmann constant. Second is canonical distribution or Boltzmann distributions. In canonical distribution system, systems in the thermal equilibrium with a heat receiver at a fixed temperature T, but with varying energy. The system can exchange energy with the receiver, so the energy is not fixed. The probability of microstate depends on its energy, and the probability pi of the system being in a microstate I with the energy EI is given by the Boltzmann distribution formula, and the formula is Pi equal to e to the power minus capital EI upon kBT, where EI is the energy of the microstate, kB well known Boltzmann constant, T is temperature, and Z is the partition function, which is defined as the Z is equal to summation of I e to the power minus EI upon kBT. Now, what is the significance? The canonical distributions describe how the probability of finding the system in a particular microstate decrease exponentially with the energy of that state. That means what? That means higher energy states are less probable than lower energy states. Third, grand canonical distributions. Applicable systems. System is contact with a receiver that can exchange both energy and particles. Both energy and particles number are allowed to fluctuate. The probability Pi of the system begin in the microstate I with energy Ei and particle number Ni is given by Pi is equal to e to the power minus Ei minus mu Ni upon kBT whole upon x, where mu is the chemical potential, x is the grand partition function. Okay, now what is the significance of this distribution? This distribution is useful for systems where both energy and particle number are not conserved, like in chemical reaction or system involving particle exchange. 4 is Fermi-Dirac distribution. System of identical fermions, that means particle with half integer spin such as electrons, that obey the Pauli exclusion principle. That means what? No two fermion can occupy the same quantum state simultaneously. Fermions have distinct quantum mechanical property that affect how they are distributed among available energy states. And the probability Fe that a quantum state with energy E is occupied by a fermion is given by the Fermi-Dirac distribution, and the formula is Fe is equal to 1 upon e to the power E minus mu upon kBT plus 1. What is the significance? This distribution is crucial for understanding the behavior of electrons in metals and semiconductor, particularly at the low temperature. Now, 5th is Bose-Einstein distribution. System of identical boson, that means particle with integer spin, that do not obey the Pauli's exclusion principle. Multiple boson can occupy the same quantum states. Boson can bunch together in the same quantum state, leading to phenomena like Bose-Einstein condensation. The probability Fe that a quantum state with energy E is occupied by the boson is given by the Bose-Einstein distribution, and the formula is Fe is equal to 1 upon e to the power E minus mu upon kBT minus 1. Now, what is the significance of this Bose-Einstein distribution? This distribution describes the behavior of the photon in black body radiation as well as other bosonic particle like helium-4 atom in superfluidity. Now, importance of probability distributions in this statistical physics. Predicting macroscopic property. This distribution allow us to calculate macroscopic property like pressure, temperature, chemical potential, etc. by averaging overall possible microstates. Connection to the thermodynamics. They provide a statistical foundation for thermodynamics, linking microscopic particle behavior to observable macroscopic phenomena. Explaining quantum systems. The Fermi-Dirac and Bose-Einstein distributions are essential for the understanding quantum systems and predicting phenomena that classical physics cannot explain. Ensemble in statistical mechanics. In statistical mechanics, an ensemble is a large collection of hypothetical systems, each representing a possible state that a physical system could occupy under certain conditions. Ensembles are used to derive the macroscopic property of system by averaging overall possible states. Given specific constants like energy, volume and particle numbers. There are several types of the ensemble, each applicable to different physical situations. Types of ensemble: microcanonical ensemble, canonical ensemble, grand canonical ensemble and other specialized ensemble. First, microcanonical ensemble. Isolated systems with fixed energy, volume and number of particles. Each system in this ensemble has the same total energy. The number of the particles and the volume of the systems are also fixed. All accessible microstates, that means all configuration of the system consistent with the fixed energy, volume and particle number are equally probable. And the entropy S in a microcanonical ensemble is related to the number of accessible microstates, that means omega, and we know the Boltzmann formula is S equal to Kb in omega. And the application of this ensemble is typically used to describe systems where no energy exchange with the surrounding occurs, like an isolated gas in a perfectly insulated container. Now, second is the canonical ensemble. Systems in thermal equilibrium with a heat receiver at a fixed temperature allowing for the energy exchange. The system in the ensemble are at the same temperature, but their energy can be vary. Volume and particle number are constant, but the energy can fluctuate, and the probability Pi of the system being in the microstate I with energy Ei is given by Pi is equal to e to the power minus Ei upon kBt by Z, where T is the temperature and Z is the partition function. Partition function Z is a crucial quantity that sums overall the possible microstate and defined by the Z equal to sigma I e to the power minus Ei upon kBt whole upon Z. It is used to calculate macroscopic properties like free energy, entropy and heat capacity. Now, the application of the canonical ensemble is ideal for system that can exchange energy with their surrounding, like a gas in contact with the thermal receiver. Third is grand canonical ensemble. System that can exchange both energy and particles with a receiver with fixed temperature, volume and chemical potential. System have the same temperature and chemical potential, but both energy and particle number can vary. The probability Pi of the system being in a microstate I with the energy Ei is equal to Pi equal to e to the power minus Ei mu Ni upon kBt whole upon x, where mu is the chemical potential and x is the grand partition function. The grand partition function is defined as the again sigma I e to the power minus Ei upon mu Ni upon kBt. This function is used to calculate thermodynamic potential like the grand potential which is analogous to free energy, but for system with varying particle number. The grand canonical ensemble is useful for system like gases where both the particles and energy can be exchanged, or in situations involving chemical reactions. Now, other specialized ensembles like isothermal isobaric ensembles, systems with fixed temperature, pressure and number of particles. The volume is allowed to fluctuate, useful for studying systems at constant pressure. Often this type of the ensemble often used in simulations of fluids where pressure is kept constant. Now, in isothermal isobaric isothermal ensemble, like those with the varying constraints on different subsystems such as the open systems or inhomogeneous material. Now, what is the significance of ensemble in statistical mechanics? Macroscopic predictions. Ensemble allow for the calculation of macroscopic properties by averaging overall possible microstates of a system. Another significant is linking macrostate to thermodynamics. By using ensembles, statistical mechanics provides a bridge between the microscopic property of particle and the macroscopic thermodynamics quantities like temperature, pressure and entropy. Different physical scenarios, ensembles are used to model different physical conditions such as the isolations, energy exchange, particle exchange. Now, thermodynamics laws and their statistical interpretation. The law of the thermodynamics are fundamental principles that describe how energy and entropy behave in physical system. These laws have both macroscopic formulation which apply directly to the observable quantity like temperature, energy and entropy, and statistical interpretation which link these macroscopic quantities to the behavior of microscopic particles. Below is an explanation of the each thermodynamics law and its statistical interpretation. First is the zeroth law of thermodynamics, everyone know. If two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Macroscopic interpretation is what? This law defines the concept of temperature. It implies that temperature is transitive property. If two systems have the same temperature as a third system, they must have the same temperature as each other, making temperature a meaningful physical quantity. What is the statistical interpretation? From a statistical mechanics perspective, thermal equilibrium means that the probability distribution of microstate in the two systems are such that no net energy is exchanged between them. The zeroth law allows us to define a temperature parameter T that can be used to describe the energy distribution of systems in equilibrium. Now, second is the first law of thermodynamics or law of the energy conservation, we well known. The change in the internal energy of a system is equal to the heat added to the system and minus to the work done by the system. That means what? In the formula form, del U is equal to Q minus W. What is the microscopic interpretation? This law is essential for the principle of conservation of energy. It is stated that the total energy of an isolated system remains constant. Energy can be transferred as heat or work, but it can't be created or destroyed. What is the statistical interpretation? In statistical mechanics, the internal energy U is understood as the average total energy of all microstates accessible to the system. The first law asserts that change in the energy are due to the change in the distribution of microstate caused by heat transfer or work done. Second law of thermodynamics. The total entropy of an isolated systems can never decrease over time. It either increase or remains constant in a reversible process. That means what? That means del S is greater than equal to 0. Now, the macroscopic interpretation. The second law states that the natural process tends to move towards a state of the maximum entropy or disorder. This is why heat flows spontaneously from the hotter object to a cooler one, and why perpetual motions mechanics of the second kind are impossible. Statistical interpretation is entropy S is a measure of the number of possible microstate omega that corresponding to given macrostate defined by the Boltzmann formula already discussed, S equal to Kb in omega. The second law implies that a system will naturally evolve towards the macrostate with the highest number of microstate, as this is the statistically the most probable state. This tendency towards the increasing entropy reflect the fact that there are many more ways for a system to be disordered than ordered. Now, the third law of thermodynamics. As the temperature of system approach absolute zero, the entropy of a perfect crystal approach a constant minimum, which can be taken as 0. That means, if S tends to 0, as T tends to 0. Macroscopic interpretation. The third law implies that it is impossible to reach absolute 0 in a finite number of steps, because as a system approach absolute 0, the entropy change for any process approach 0. And statistical interpretation said at absolute 0, a system is in its ground state, meaning there is only one possible microstate, that means the ground state itself. Since entropy is measure of the number of accessible microstate and there is only one microstate at absolute 0, the entropy approach 0. That means S equal to K B I N 1, that means 0, in the place of omega putting 1. This reflects the idea that an absolute 0 all particles are in their lowest energy configuration with no thermal motion, and thus the system is perfectly ordered. Now, quantum statistical mechanics. Quantum statistical mechanics is a branch of the statistical mechanics that applies the principle of quantum mechanics to system with a large number of particles. It is used to study the behavior of quantum systems, particularly at very low temperature where quantum effect becomes significant. Now, key concept: quantum states. In quantum statistical mechanics, the microstate of a systems are described by quantum state, which are governed by the wave function or quantum operators. Indistinguishable particle. Unlike classical particle, quantum particle can be indistinguishable. This leads to different statistical for different type of particle, like boson. Follow the Bose-Einstein statistic where multiple particles can occupy the same quantum state. Fermion. Follow the Fermi-Dirac statistics where no two particles can occupy the same quantum states. Bose-Einstein condensations. At very low temperature, boson can occupy the same ground state, leading to a macroscopic quantum state known as Bose-Einstein condensate. Fermi-Dirac distribution. The statistical distribution that describes the occupancy of energy state by fermions at a given temperature, crucial for the understanding the behavior of electron in solids. Quantum statistical mechanics is essential for the understanding the phenomena such as superconductivity, superfluidity, black body radiation and the electronic property of materials. It provides a framework for studying systems where quantum effects dominate, particularly at microscopic scale and low temperature. Now, phase transitions and critical phenomena. Phase transitions and critical phenomena are important concepts in statistical physics that describe the behavior of physical system as they undergo change from one phase to another phase, such as from solid to liquid or liquid to gas. These transitions often involve dramatic change in the physical properties and characterized by critical points where this change becomes particularly significant. Phase transitions. A phase transition is a process where a system changes from one phase to another, such as from solid to liquid or melting, liquid to gas, vaporization, or from one crystalline structure to another. During a phase transition, certain physical property of systems such as density, magnetizations or specific heat change abruptly. Now, the types of the phase transition. First order phase transitions. In a first order phase transitions, the transitions occurs with discontinuous change in some thermodynamic quantities such as density and magnetization. There is usually a latent heat associated with the transitions, meaning energy is absorbed or released during this process. For example, melting of ice, boiling of water and the transitions between the different crystal structure in solids. Now, second order or we can say continuous phase transitions. In second order phase transitions, the transition occurs without any latent heat and is characterized by continuous change in the order parameter, a quantity that distinguishes different phase like magnetization and ferromagnetic. The second derivative of free energy typically diverges or show a peak. Example, the transitions from a paramagnetic to ferromagnetic state at the Curie point or the superfluid transitions in the helium. Now, what is the critical phenomena? Critical phenomena refers to the unique and universal behaviors observed near the critical point of second order phase transitions. Near the critical point, certain physical quantities exhibit power law behavior and the system shows scale invariance, meaning that it looks the same at all length scale. Key features are divergence of correlation length. As the system approaches the critical point, the correlation length, different parts of the systems, that means a measure of how correlated different parts of the systems are with each other, diverge. Measuring fluctuations occurs over increasingly large distance. Critical exponents. Physical quantity near the critical point exhibit power law behavior characterized by critical exponent. For example, the specific heat might diverge as C equal to T minus Tc to the power minus alpha, where alpha is the critical exponent and Tc is the critical temperature. These exponents are universal, meaning they do not depend on the microscopic details of the system, but only on the general features like dimensionality and symmetricity, etc. Order parameter. The order parameter is a quantity that change from 0 in one phase to non-zero in another, characterizing the different phase. For example, in ferromagnet, the order parameter is the magnetization, which become non-zero below the Curie temperature. Scaling laws. Near the critical point, physical quantities follow scaling laws, where the critical exponents are related to each other through these laws. For example, The relation between the specific heat exponent alpha, the susceptibility exponent gamma and the correlation length exponent V is given by the Rusbrook's inequality alpha plus 2 beta plus gamma is greater than from 2. Universality. System with the different microscopic detail can show the same critical behavior if they share the same symmetry and dimensionality. This phenomena is known as the universality. Applications of statistical physics in various fields. Statistical physics, which connects microscopic particles behavior to macroscopic physical property, has a wide range of application across the various scientific and technological fields. Here are some key area where statistical physics plays a crucial role, and these areas are condensed matter physics, magnetism, superconductivity, quantum Hall effect, thermodynamics and heat engines, heat transfer, statistical mechanics of gases, kinetic theories, biophysics, biological networks, etc., population dynamics, information theories, data compressions, material science, polymer physics, crystal structure, amorphous solids, glassy solids, astrophysics and cosmology also inside this black body radiation, star formation, cosmological models, chemical physics also, that means reaction rate, phase equilibria, statistical thermodynamics, computational physics, Monte Carlo simulation using the statistical method to simulate and analyze complex physical systems that are difficult to solve analytically. Molecular dynamics, simulating the motion of atom and molecule to study the property of the materials at the atomic level. Economics and social science is also a wide area. Social networks and game theory also is the very important applications. Now come to the future direction in statistical physics. Future direction in statistical physics. The future of statistical physics is poised to tackle some of the most pressing scientific and technological challenge of our time. By integrating new computational tools, exploring complex systems in new ways, and applying the statistical principle across diverse fields, researchers will continue to push the boundaries of our understanding, leading to innovations in every from quantum technologies to sustainable material and beyond. So, thank you very much, and thank you again for being here today. Thank you.